Hi, so this is homework 3 part C. What we're going to do today is we're going to use the route Hurwitz criteria to find the maximum proportional controller gain in relation to the process gain for three identical first order systems in series under closed loop control, which we used in described in part A, or I think it was B. And then we're going to use a code to verify the stability characteristics computationally. So I've already written our equation that we found earlier in part B, and what was it? And what we're going to do today is we're going to utilize this entire section, and we're going to implement it um, into that equation. So what we're going to end up with is we're going to have H3, which will equal KC KA, all of that, and we're going to have tau cubed S cubed plus 3 times tau squared S squared plus 3 times tau times S plus 1 plus our KC K value. And then this is going to be multiplied by our A over S. And then something we want to point out, use a different color, is that in this entire denominator right here, we'll have no positive roots. Okay. What we want to go to next is our route Hurwitz criteria. And basically how we want to set this up is we have our okay, so now what we're going to do is we're going to have our t cubed 3 tau I believe this is 3 squared and then 1 plus kck, and then we'll have 0 0 0 0. Basically what we're going to do is going to subtract this. It's going to be multiplied, and then it's going to be added. And essentially what we're going to find is we're going to find roots. So we're going to label as B1 and B2. And going through the whole calculation of this, we end up with just simplifying to B1 equals 1, and then B2 equals 0. And then we do have two other roots we want to find, C1 and D1. However, we're going to look at that later. Okay, so now what we're going to do is we're going to go ahead and find the equation for B1. So, essentially what we're going to have is 3 tau squared times r tau cubed minus tau cubed times 1 plus kck all over 3 tau. I hope I changed the DPS in my mouse. So now what we're going to also do is recall C1. Basically what this one is just 1 plus kck, and this is basically what the pattern that we've been seeing pretty much everywhere. And this is going to be minus 3 tau squared. However, it's going to be multiplied by our B2 value, but B2 is 0. So what we are left with is 1 plus kck, which has to be greater than 0. And that basically means that kck has to be greater than -1. And then back to our b1 values, or b1 equation, we want to go ahead and simplify that down. So when we simplify it and get rid of something, oh, I believe this is supposed to be squared, and then, oh, yep, it's supposed to be multiplied by 3 tau. I'll double check that in a sec. But B1, so basically what we're left with is tau minus 3, or no, tau times sorry, that just had to double check, 1 plus kc k all over 3, which is going to be greater than 0. And our objective is essentially to get this kc by itself. So if we simplify this down, we're left with 9 minus tau 1 plus kck. Actually, there's no tau. Then 0, and so now we're left with 8 minus kck is greater than 0. And basically, if we get kc by itself, we're left with, oh, draw it backwards so I don't get confused. 8 kck, and then left with 8k is greater than, oh, that's horrible, kc. And so using our Routh-Hurwitz criteria, we find that the maximum proportional controller gain is basically kc has to be less than 8 over k. And then we're going to get into the coding section of this to apply all this. Alright, so now what we're going to do is we're going to go ahead and start with our coding section of this. So I've gone ahead and made our variables that we need. So our k value set to 1, kc, which is 8 over k plus 0.1, and then our tau is set to 1.5. So we want to go ahead and we're going to do our other components that we want to set. So this can be k divided by our tau plus s plus 1. And that's going to be cubed, as we remember from part thing B. GC, we have it set to kc. And then we're going to do our G in terms of our closed loop. So I'm going to set that to GCL. And that is GC plus, it was 1 over GC times GP times KC, or actually I think this is GP. And we're going to set TH equal to sim, where we're going to have GCL, have lambda in terms of 1 and we're going to set n equal to 5,000. Our dt is 0.1, and that should be okay, so this is actually 1 plus GC plus GP. There's no KC involved. And that should work. Yep. And then this is a relatively simple code today. So we're just going to go ahead and plot our make subplots. Or is it subplot? Oh, yeah, it is subplots. Then fig dot add underscore scatter, where x is our t, y is h. We're gonna have mode set to, oh god, lines. And then just to make it a little easier to see, we're gonna update the layout with our width being 100 and our height being 400. It's not supposed to look like that. Okay, one more thing. It's supposed to be multiply, and then if we run all, I found another multiplication sign that was supposed to be multiplication instead of addition. There we go. So now we have our graph, and this is the plot that we see. So this is at k equals 1, and basically what that does is now it's saying it's k c equals 8 over 1.1. So what happens if we suppose make it 0.1, and it becomes very thick, and that's a little bit of a pattern that we see here, where the lower k goes, the more unsteady the system becomes, due to the fact that Kc is a lot higher value. However, as we approach Kc being closer to 1, so suppose we make it 5, we see that it's starting to thin out here. So let's make it actually 1, so that would be 7.9, and that would mean that k plus 0.1 would be 8, so this would make Kc 1, and we can see that this is the plot we're going to be looking for, and this is where it's steady.